So hello guys, welcome to the continuation of phase transformation. And with this, we're going to handle that is lecture two, as in part two of this course, and it's taken by Stephen Onoma as the original content creator of Perform YT channel. And please kindly subscribe and like for more of this, and also share for your friends. So with lecture two, we are going to look at phase diagram as we discuss some definitions in the first lecture that we did. So now let's get going. So when we talk about phase diagrams, I told you that this course, which is phase transformation, it involves two things. We have the phase transformation itself and phase diagram. So what are you going to get? At the end of this lesson, you're going to learn how to find the phase of a phase diagram and also find the liquidus temperature, the solidus temperature, and also find the composition and amount in the phase diagram. So let's get going. So now when we talk about phase diagram, it is what? A graphical representation of the phases that are present in a material at various temperature, pressure, and composition. And it's usually described the equilibrium condition, right? As we heard from the first lecture that I gave you, and also sometimes non-equilibrium condition and also known as well. It indicates the melting, that is the solidification temperature of the constituent. It indicates the composition of the alloy, where solidification begins and temperature ranges which occurs. So now, phase transformation is an alteration in the number and or the character of the phase in the system. Yeah. So normally with phase, it's just a graphical representation of the phases that are present in the material at various temperature. Now, phase diagrams. The diagrams representing conditions of temperature, pressure, composition at which one or more phases exist. So depending on the temperature and the composition, it will give you different phase diagrams, right? So take that into consideration. So now, this is the phase diagram of water. So as you can see, we have how many phases here? We have three phases here. We have the liquid phase, the solid phase, and the vapor phase. Now, when we take this, so when we do that, when we take this fusion curve, we know that it has what two phases because here for this curve, we have the solid phase and the liquid phase. And also this vapor pressure curve also has two phases, which is the liquid phase and the vapor phase. But when you talk about the triple point, it has three phases because we know at this point we have the solid phase here, the liquid phase, and the vapor phase, making it three phases. Now when you talk about the sublimation curve, we have the solid phase and also the vapor phase, making it two phases. So you should note that at each curve we have different phases, right? And when you look at the liquid, with here it's only one phase. With the solid part, it's only one phase, and with here the vapor part also has one phase. Now let's look at something. So we are going to describe the phase diagram of water into detail. So let's read something here. Some important features of what? Water system. Now, possible phases. We know we have three phases as I told you. We have the ice, water, and vapor. So how many phases? Three phases. Now let's look at this. There are three curves. That is, we have the metastable curve and the stable curve. I will show you the metastable curve. So when we talk about the metastable curve, this curve is supposed to pass here, which is the sublimation curve. But there's another curve created here, which is not part of the main curve. So this becomes a sublimation curve. So let's see from here. So now, the curves are three stable curves throughout. OA, which is OA, the vapor pressure curve. We have OC, which is, okay, let's talk about OB, the sublimation curve. And we have OC, which is the melting point curve. So these are the three curves. These are stable curve. And when we talk about the metastable curve, is what? OA, as I told you. It doesn't form part, but it creates an alternate way which doesn't form part of the curve, which represents it. So that one to become what? A metastable what? Curve. Now, when we talk about metastable curve, it's a system. It's a staging with a system is stable, but it can be more stable if it's supposed to cross an energy barrier, right? Yes. So now look at this area, three areas representing ice, water, and vapor. So for the phase diagram of water, we have three possible phases and three stable curve with one metastable curve. Now look at it, the triple point where all the three phases are in equilibrium. So at the triple point, you can have liquid, solid, and gas. So the melting point curve OC slopes towards the pressure axis, has negative slope. What does it mean? Showing that the melting point of ice decreases with what? Decreasing temperature. So when you increase the pressure, so when you increase the pressure, the melting point of the ice start to decrease. You should note that it's very important. About the one component phase diagram. When we talk about one component phase diagram, it means that it's just water is one component phase diagram and what? That is SiO2. So we are going to look at it and I'll explain something here with this. We are going to understand the degree of freedom that we did in lecture 1. Yes, so the degree of freedom, and you understand how to find the degree of freedom. And I told you about if the degree of freedom is 0, it's at the triple point. If it's 1 and 2, you understand why this. So when we take the quart, that is SiO2 system, let's look at it. We are going to consider A at this side. So we have one phase here, another phase here, another phase here. We have another phase, another phase, another phase, another phase. So please, can you please tell me the number of phases that we have here? Please, can you comment under the comment section? So now, with two variables, that is pressure and temperature. So pressure and temperature. What does it tell you? It means that the intensity property is 2. You should know that from the lecture 1, the intensity property of this becomes 2 because we have pressure and temperature. So now, this is one component, that's SiO2. We have 7 different phases. So let's check whether you had it correct. So it's 7 different phases because we have 1 here, 2, 3, 4, 5, 6, and 7 different phases. Now we are going to find something which is at point A. Now we are going to find the degree of freedom. So now at point A, now C is the composition, and we know that it's one component. P is the number of phases. When you look at here, it has only one phase here, which is a coesite. And I told you that the vein, which is the intensity property, pressure and temperature is intense. They are all intensity properties. So making the intensity property being 2, that's why we have 2 here. So when you solve this, you're going to get that since the composition is 1 and the phase is 1, plus this, we are going to have the number of that's the degree of freedom being 2. And when the degree of freedom is 2, how do you describe this? It means that it's divariant area, 2 variables to define a position in a coincident stable field. Right? Yes. So for a single phase, the degree of freedom is 2. Only if the intensity property is pressure and temperature, or pH and EH. We did that in lecture 1. Now let's take another one. What if the variable has been changed to another place? So this is on this curve, right? It's on this curve. So on the curve, on this curve. Now, so on this curve, let's check. Let's see, it's two variable, one component. The phase is what? 7 down. Please, how many phases do we have here being on the curve? Can you comment on the comment section? So here, let's see. The number of phases here is 2, because let's see, we have the coincidence and the quartz. This line, this curve, is between this phase and this phase. So it means the number of phases there is 2. Then you know that the intensity property, which is the thing, is 2. The phase is 2, and the composition is one component. So it is 1. So when you do that, the degree of freedom is 1. That's why I told you in the previous, that's lecture 1, that when the degree of freedom is 1, it's on the curve. And when the degree of freedom is 2, it's on a specific phase. So now that means that when the degree of freedom is 1, what does it mean? It means that it's what? A univariant area. One variable to define the position. on the coincide and quartz phase boundary. I hope you understand that. So you should know that when it is 2 is die, when it is 1 is uni. Now let's look at when we have the triple point. So the C is at the triple point. Now please, can you please comment the number of phases we have here? Yes. Yeah. So the number of phases that we have here is 3. And the composition is 1. So you know here we have the coincide, the quartz, and this alpha quartz and beta quartz. So therefore the degree of freedom is 0. And it is invariant. Triple point do not need any variable to define equilibrium between the coincides alpha and the beta quartz. So you should note that when the degree of freedom is 0 is on what? The triple point, which is the invariant area. And when it is 1, it's on the curve, which is the uni. When it is 2, a specific phase, which is die. So let's move on. So now we have types of alloys. Yes, we are going to the general types of alloys. Now, when we talk about alloys, the uniform mixture of 2 or more metals, being a metal or a non-metal. So now, there are 2 general types of alloy having phase diagram, which is the substitutional and the interstitial. So with this, in principle of materials, if you've done that course, you understand the substitutional and the interstitial. Now, let's look at let's explain the substitutional. Alloys have elements which are incorporated into a regular lattice position within the unit cell. Example, we have tin and zinc alloy forming with copper. So we have brass and bronze. So with this, they sit as what? The occupying site of the atom, right? And this, we have the brass and the bronze. So tin and zinc in addition to copper to form bronze and brass. But with the interstitial alloy, they sit as what? Unoccupying site, which is the interstitial site. So have elements which are incorporated into the interstitial site of the unit cell. An example is the iron in carbon in iron to form steel. Let's leave that. So now we're going to look at working with phase diagrams. So with working with phase diagram, what do you need to know? We need to know the overall composition, the solidus, the liquidus, limits of solubility, chemical composition of phases at any temperature given, amount of phases, invariant reactions, development of microstructure. All this we are going to get through. Yes, but I think that one will be in lecture 3. We'll cover up to this side for the lecture 2. And lecture 3 will continue. So with this, it's a nice course. You understand. So let's get going. And also we need to know the cooling curve, differential scanning, calorimetry, chemical analysis, differential thermal analysis, metallurgy or petrolography, energy dispersive X-ray spectroscope, electron microbe analyzer, X-ray diffraction, and transmission electron microscope. So now let's look at working with phase diagrams. This is 2 components. The one that we did was 1 component. This is 2 components. So because I'm doing cooling curve, so with cooling curves, it deals with liquidus and solidus. Let's try to explain what is solidus temperature and liquidus temperature. So when we talk about liquidus temperature, is the temperature above which a material is completely liquid. So it means that when, let's say this is a line and this is the liquidus temperature, it means that here there are only liquids here, only liquid that you can find here. The same applies to solidus. It's above which the alloy is 100% solid. So when you have this being the solidus temperature, above this we have 100% solid. And the freezing range is then the difference between the liquidus temperature and the solidus temperature where the 2 phases exist. Let's know that. So let's take some example. So this is a series of cooling curve. Now look at this. We are going to understand something here. So now this is the liquid, representing the liquid, and this is what? Alpha. So that means that at this stage we have the liquid and alpha existing. So for us to find the liquidus temperature, when you are coming here, when it hits here, this becomes the liquidus temperature. So this side becomes the liquidus temperature, and here becomes what? The solidus temperature. To find the freezing range, that means we are going to subtract this from this to get a what? Freezing range. Let's do the cooling curve. Now, from lecture 1, I taught you how to do the cooling curve. So whether you are cooling it from here, so from temperature against time, and it's from liquid. So from liquid and it hit at this point, at temperature this, then it's maintained for a certain time, then it cools and hit at this point and changes to solid. So there's the solidus and there's the liquidus. To find the freezing range, as we said, to be 120, 200, that's 1280 degrees minus 1240 centigrade, giving you 40 centigrade. That is the freezing range. And note this is percentage in what? Nickel. So I will explain that. So that means that, let me explain something here. When you talk about, you also consider the composition. Now, when you talk about weight percent of nickel, it means that with here, this represents the nickel. So with this, we have 20% of nickel here and 80% of copper. With here, 60% of copper and 40% of nickel. Here, we have 80% of nickel and 20% of copper. So we should pay attention to the composition. Now let's look at cooling curves. So with lecture one, I tried to explain cooling curve, but here let's look at the main overview of cooling curve. So pure metal solidifies at a constant temperature, which is known as the melting point. Binary alloys solidify over a range of temperature. So they don't have a fixed temperature for them to solidify, right? Yes. So these are the cooling curve. Now when you combine cooling curve together, then we get a phase diagram. So this is a cooling curve for pure copper, and this copper to 8, that's 80% of copper and 20% of nickel, giving 100, 60% and 40. Then when you do this, then when you put all together, then you get what? The phase diagram. So please, this cooling curve is very simple. You can go over again when you watch lecture 1. I explain how to produce the cooling curves. Now we are going to do the isomorph. That is the isomorph phase diagram. Iso means same. When we talk about iso, that means that two compositions come together to form one composition. So let's look at something. So when two elements or two compounds are present in material, a binary phase diagram can be constructed. In an isomorph binary phase diagram, only one solid forms two components in the system, display a complete solid, but solid solidity. So as I told you, one solid, then two. So it's one solid they form, but it's due to two solids coming together as like it can be like a vector reaction. Example is copper nickel and copper oxide and magnesium oxide system. So look at this. So we are going to look at this is let's look at something here. So note this. What I want you to notice that they are trying to explain something. See their composition. This is temperature against composition. So with that, we need to know that the composition can be in weight percent or what? Mole percent. So let's take note of it. So the composition can be in weight percent or mole percent. It's the same. Now, with this, that is the mole percent of what? Magnesium oxide. It means that this number represents what? Magnesium oxide. So when you talk about it, we have 20% of magnesium oxide, but 80% of nickel oxide as compared to